Should we start? Okay. All right, so let me introduce this group GL2 plus R. Consists of all matrices A, B, C, D, real entries, and AD minus BC is positive. So you can verify that that's a group. And GL2 plus R acts on the upper half space. The upper half space is the set of all complex numbers, x plus iy, with x, y real, and y positive. So collection. So pictorially, you have the complex plane, and the upper half space is this region without the real line. So this is your upper half space. And the action of the matrices is given by the fractional linear transformations of this type, which we already kind of saw. And you just have to check that this is an action. So you have to check that the imaginary part of AZ plus B over CZ plus D, what is that? Well, if I multiply top and bottom by the complex conjugate of the denominator, I get CZ plus D squared. And I have AZ plus B times CZ bar plus D. And you calculate the numerator AZ plus B times CZ bar plus D. Turns out to be AC mod Z squared plus A d z plus B C Z bar plus BD. That's what the product is, and we're interested in the imaginary part of this. So since this is a real number and this is real, the imaginary part will only come from here, and the imaginary part is easily seen to be AD minus BC times the imaginary part of Z divided by mod CZ plus D squared. So because this is positive, AD minus BC is positive, this gives us a nice action of GL2 plus R on the upper half space. Okay, so that's simple enough. These transformations, these fractional linear transformations, they're often called Mobius transformations or fractional linear transformations. Or Mobius transformations. Observe that the scalar matrices lambda times I, with lambda positive, well, the lambda can be real, I guess, and the determinant would be lambda squared. So lambda is a real number. These operate trivially. So these scalar matrices act trivially on H. We're going to look at the upper half plane as an open subset of the complex plane endowed with the usual topology. Okay. So there are all these matrices, there are all these elements in the group that act trivially. So in order to kind of cut down the size and get what's called a faithful action means that the only element in the group that kind of fixes the whole thing is the identity element. So we want to get a faithful action. We mod out by all the scalars. So it is convenient to consider, we sometimes consider PSL2R, which is SL2R. So this already tells you to mod out by scalars, modulo plus or minus the identity element. And it turns out that the action, this acts faithfully on the upper half plane. That means that if G is an element of PSL2R, such that G acting on Z is Z for all Z in the upper half plane, then G is the identity element. That's what we mean by faithful action. Moreover, the action of PSL2R is transitive. I'll leave this as an exercise for you to do. Moreover, this action is transitive. That is, if I have two elements, Z and W, sitting in the upper half plane, so this is i.e., if given Z and W in the upper half plane, there exists a group element in PSL2R such that G takes Z to W. And to see that, maybe it's not a bad idea to do this. To see this, we will show that any element can be actually taken to I, which is square root minus 1. To show this, it suffices to show, it suffices to take, to show that there exists a G such that G takes Z to I. So for any complex number Z in the upper half plane, if I can show this, then we can easily we take G1, which takes W to I, and then we apply G in one inverse. G then takes Z to W. So it suffices to do this special case when W is I. And for that, this is pretty easy. So if Z is equal to X plus IY, Y positive, we look at the matrix and let this act on I, and we see that simple calculation shows that this is X plus IY. So I've managed to show that there's an element taking I to my prescribed point, and both these elements are inside PSL2R. So this is in PSL2R. And so in order to find that G that you are looking for, all you have to do is take the inverse of that, and that would do it. Okay, so it's a transitive action. So the action is transitive. And so yesterday we saw that when you have a transitive action, the upper half space can be represented as a coset space of PSL2R. So we take the stabilizer of I, for example, and mod out by that stabilizer, then it turns out that that quotient space can be identified homeomorphically to the upper half space. And that's an important point of view in the Langlands program, as I was trying to emphasize earlier. Okay. Yeah, so I'll leave this as a following exercise, which you can perhaps discuss in the afternoon, and that is that the map Z goes to Z minus I over Z plus I is an analytic isomorphism of the upper half space with the unit disk. The unit disk. So I'll leave that for you to check. Firstly, that this map actually takes upper half plane into the unit disk, and that it's an invertible map, that you have to check all that. So I'll leave that to you to do. This fact will be useful in a moment, because I'd like to understand what are the analytic automorphisms of the upper half plane. What are the maps of the upper half plane, which are analytic maps, which are invertible also, analytic homeomorphisms. So what are the analytic automorphisms of H? So maps that go from H to H, which are holomorphic maps. So in order to do this, I just need to make sure that everybody, a small review of some complex analysis. So an important theorem in complex analysis is what's called the maximum modulus principle. Maximum modulus principle. And this principle basically says that if you have a function in the complex plane defined on some region R, like closed region like this, and I'm looking for the maximum of this function as Z ranges over all the elements of this region, that the maximum is actually attained on the boundary. So we use this. This is the boundary of R. A remarkable theorem in complex analysis. So I'm hoping that that's just review, that you've seen this before. A classical application of the maximum modulus principle is to what's called Schwarz's lemma. which is an interesting lemma in its own right and worthy of independent interest. So Schwarz's lemma. Suppose f of z is an analytic function with mod f of z less than or equal to 1 for all z inside the unit disk. Let me take the closure of the unit disk because I defined it as the open disk there. And suppose further f of 0 is 0, then this bound can be improved. Can be improved. That's a beautiful theorem in its own right. And the proof is using the maximum modulus principle. Consider the function g of z equal to f of z over z. So this is for z not 0. And for z equal to 0, just define it as f prime of 0 for z equals 0. Because f of 0 is 0, we'll define f of g of z to be f prime of 0. F is an analytic function, so the derivative exists and so on. So it's easily checked that this is now analytic. Clearly, G is analytic. And by the maximum modulus principle, the maximum of G of z the maximum G of z on the closed disk is actually attained on the boundary. But this boundary is just the set of points where mod z equals 1. And there I'm away from 0, so that's just that, which is just max. But I have this bound. Okay. And therefore, G of z, which is f of z over z, in modulus is less than 1. Therefore, f of z is less than mod z. So it's a beautiful, cute thing. In somehow, this crude estimate can be sharpened to this result. So it's a very useful tool to have. So we'll use Schwarz's lemma to answer this question of what are the analytic automorphisms of the upper half plane. In fact, we'll pull the following theorem. The group of analytic automorphisms of the upper half plane is isomorphic to PSL2R. So that's why this group is important. Okay, so let's see. Let's try to classify. Let's take an automorphism. Then write phi of I as A plus BI with A and B real. So I is an element in the upper half plane, so it goes to another element in the upper half plane. B is positive, so it be real, be positive. And we look at the map. Consider the map psi of z equal to phi of z minus A divided by B. Okay, consider this map. Then, since phi of I is A plus BI, this takes psi takes I to I. Then, psi of I is equal to I. Okay, now let H of Z be the map Z minus I over Z plus I, which I gave in the previous exercise. This is an analytic map. From H to H. That's because the problem point is minus I, but we're not in the upper half. We're in the upper half plane, so minus I is not a problem. So it's an analytic map. And we consider the following. What is it? Oh, for us, what? I can't hear. Huh?
The map H defined will be analytic map from upper half plane to unit disk. The H you defined Z minus I by Z plus last line.
Oh, this? Oh, yeah, sorry. This. Oh, you mean this is a D? Is what? Yeah. Sorry. Yes. That's you're right. Thank you. Because of the exercise that I gave you. Yes, exactly. Thank you. Yeah. All right. So now, okay, put G of Z to be H composed with psi composed with H inverse of Z. Okay, so H is a map that takes the upper half plane to the unit disk, and the H inverse therefore takes the unit disk back to the upper half plane, so we're back in the upper half plane from this one. Psi then takes the upper half plane to the upper half plane, and then H then takes it back into the unit disk. So G is a map from D to D. Then G is a map from the disk to the unit disk. Moreover, because everything is analytic, the composition of analytic maps is analytic, okay? So everything is analytic, so this is an analytic map. And moreover, let's look at G of 0. Is equal to H psi H inverse of 0. So H inverse of 0 is I, because when is H 0? When Z equals I, okay? H inverse of 0 is I. So this is equal to H psi of I. And psi of I, I'm fixed it so that it's I. So this is H of I, which is again 0, right? So G of 0 is 0. So I have a nice map, perfectly tailored for Schwarz's lemma. So by Schwarz's lemma, because G is going into the disk, G of Z is always less than Z. We see that G of Z, in fact, is bounded by Z. Okay. Now we could have applied Schwarz's lemma to the inverse map. To the inverse map. So to the inverse, to G inverse. So how do you take the inverse? You take H psi inverse. H inverse. Okay, so that's the inverse map. Okay. This is equal shows that, so applying it to this, and which satisfies the same properties, which also the conditions of Schwarz's lemma. We see that G inverse of Z is also less than. And so from putting everything together, since Z is equal to G inverse of G of Z, we see that right, the absolute value of Z is equal to the absolute value of G inverse of this. Now I apply Schwarz's lemma on this part, which tells me that it's less than the argument. So therefore, mod Z is less than or equal to mod G of Z, and mod G of Z is less than or equal to that. So we combine these two to get that mod G of Z is actually mod Z. And so G of Z must be equal to Z times some root of unity. Well, not root of unity, it's some number which has absolute value 1 for some theta real. Okay, now the inverse map of H of Z is easily calculated. I'll leave that to you to do. We have H inverse of Z equals I 1 plus Z over 1 minus Z. And so, if I want to calculate psi of Z, so psi is given here. So from the fact that G is equal to H psi H inverse, I can calculate psi in terms of these, okay? Which we know is equal to H inverse of e to the I theta. See, the theta, of course, will depend on Z. I'm not going to carry that messy notation. Okay. And because I know H inverse explicitly, here it is, okay? We write it down. And when you work it all out, I'll leave the messy details to you to check. You end up getting I e to the I theta plus I times Z plus e to the I theta minus 1 divided by minus e to the I theta plus 1 plus I e to the I theta plus 1. And multiplying top and bottom by e to the minus I theta over 2, we don't change anything. So multiplying top and bottom by that, or divided by 2i. So divide this by 2i. So that we end up getting that this is actually equal to cos theta over 2 z plus sine theta over 2 divided by minus sine theta over 2 z plus cos theta 2 over 2. In other words, psi can be thought of as corresponding to PSL2R. Oops. That is, psi corresponds to this matrix cos theta over 2, sine theta over 2, minus sine theta over 2, cos theta of 2, which has determinant 1, and that's the action on the upper half space. So the action of psi is given by an element of PSL2R. So this shows that what was psi? Remember, there was this. I started off with take the analytic automorphism, which was phi, and I defined psi in terms of phi. But now I work backwards and see that I can rewrite phi in the same way. So working back to phi, finally, we can write 5z as root b psi of z. So it's again to be thought of as the matrix root b a over root b 0, 1 over root b. B being positive, remember, acting on z. So we identify phi with an element of PSL2R. So any analytic automorphism of the upper half plane corresponds to transformation of PSL2R. All right, so that's a nice theorem. It's a nice theorem combining some interesting ideas of complex analysis along with the group action of PSL2R on the upper half plane. Now, let me just make some general remarks. So PSL2R is, as I mentioned earlier, PSL2R is somewhat is too large a group. We look at discrete subgroups. So let me just give you the definition of a discrete subgroup. So if G is a topological group, a subgroup gamma of G is called a discrete subgroup if for any sequence of elements, if for any sequence gamma n's inside gamma n's tending to 1 in the topology, of course, is eventually constant. If any sequence gamma n with gamma n tending to 1 is eventually constant. In other words, there's a neighborhood of the identity which contains only finitely many elements. So this is the definition of a discrete subgroup. In a sense, one of the perhaps the success stories of 20th century mathematics is that we now think of abstract groups and discrete subgroups as analogous to the ordinary integers versus the real numbers. So somehow that analogy will play off. And just as number theory has been preoccupied with the study of integers, number theory in the large, namely Langland's program again, would be interested in studying discrete subgroups of reductive algebraic groups. That's the general philosophy. So that would contain interesting arithmetic is a general philosophy that has certainly driven much of 20th century mathematics. Okay, so as an exercise, for example, I let you to do that with this definition in place, that SL2Z is a discrete subgroup of SL2R. Much of many of the advances of in number theory have been married with ergodic theory as well, and this point of view of looking at discrete subgroups as somehow generalizations of integers has been a dominant motif in that study. Okay, now we will move into fundamental domains. So section 2, fundamental domains. So I'll spend a little bit of time here because I think without understanding fundamental domains, you're not going to do modular forms at all. So better to get some familiarity with that. So here's the formal definition. If gamma is a subgroup of SL2Z, and F is a subset, is a closed subset with connected interior, so closed set, connected interior, satisfying, we say if gamma is a subgroup and F is a subset which is a closed set with a connected interior satisfying three properties. One, any Z in the upper half plane is gamma equivalent to some W in F. 2, no two interior points are gamma equivalent. No two interior points of F are gamma equivalent. And 3, the boundary of F is a finite union of smooth curves. Okay, so here's the point. Remember yesterday we talked about, we talked very briefly about groups acting on sets and topological groups acting on topological spaces. So here we have a subgroup, a discrete subgroup inside SL2Z. And we know that gamma acts on the upper half plane. And we then like to study the collection of orbits. Okay, so this is the orbit space. But it's not just as a set, but as a topological space. We'd like to consider this as a topological space. And we want to consider this as a topological space and with a nice topology, which makes all this work kind of neat. So the idea then is to look for a nice description of the orbit space that you can visualize. So here we are sitting in the upper half plane, and the whole group is acting on the upper half plane, but it's moving points all over the place. We'd like to identify a particular region of the upper half plane which gives us the set of representatives for this action. Okay? And in such a way that you don't want your representatives to be all over the place, you want them to be in some sort of continuous manner. That's why you have a connected interior. And it's got to be a closed subset, so that, and then every point in the upper half plane has a representative in the fundamental domain, and any 2 points inside the fundamental domain which are equivalent, that can't happen. So, and then that means if they're interior points and they're equivalent, they're really sitting on the boundary. They can't be interior points. And then finally, you have this kind of. So that's the idea behind the theory of fundamental domains. Let me just give you an example. We'll start with a baby example. Let gamma infinity be the collection of matrices of this type. Well, this gamma infinity is, of course, isomorphic to Z. You take a natural number or an integer n, you map it to this matrix, and so the matrix multiplication, everything tallies. This is an isomorphism. So gamma infinity acts on the upper half plane via what? Via Z goes to that matrix 1, 1 n 0 1. What it does is just shifts the thing by unit length, by n units.
Might have to take minus identity.
What do you mean minus identity? Oh, okay, well. No, I'm letting all the n's be. You mean for this isomorphism?
No, it's in itself not the same. So the omega is plus or minus of those relations.
You want me to take both plus and minus? It's not, well, okay. Well, you just want me to put plus or minus here? Yeah, I mean, usually this plus or minus identity is just trivial action, so it's not really terrible.
So what you write number 1 there,
Mm-hmm.
you see in plane is gamma equal
To a point. Oh. Yeah, to a point. Sorry, I'm abbreviating it, so I should have. Yeah, so if we take a look at this, then we see that this is just translation. So everything is generated by the unit translation by 1. And therefore, if I was looking for a fundamental domain, so if I was looking for a nice description of this, the fundamental domain for this action, I could take any strip of length 1, right? I mean, so this is 0, this is 1. And of course, this line is not here. And this region, and of course, the boundary, so this is a closed region, closed in the sense of closed in the relative topology, right? Closed region in the upper half plane. no two interior points are equivalent under this action, and therefore this satisfies these three axioms for fundamental domain. The boundary is just two lines, certainly smooth curves. No two interior points are equivalent, and any point in the upper half plane can be, after suitable shifts, can be brought to into this region. So this is a very simple description of a fundamental domain. Obviously, it's not unique. I could have taken this from -1 to 0 and taken this part too, as long as it's just one strip. Or I could have taken even from -1/2 to 1/2, as long as the strip is length 1, right? I mean, so I could have taken many different regions in the upper half space as fundamental domain for this action. So the fundamental domain is certainly not unique.
So what is the meaning of minus is there in the notation, which is as
Where?
What is the plus minus sign in the notation?
Well, he wanted me to put it in, so I put it in just to satisfy. I really didn't want to put it in there. It just means plus or minus identity. He was worried about plus or minus the identity. I could have had both minus signs too, as sitting inside SL2Z, right?
No, if you put the minus on the minus 1, then it's not that Z goes to minus Z. Okay, yeah.
It does, yeah? Yeah, it's okay, yeah. So no, this minus sign business is really irrelevant, almost. That's why sometimes people mod out by plus or minus, not to have that discussion, yeah. Okay, so this is an example of the fundamental domain for this particular action. So let's do a little harder. Maybe I'll keep all these conditions on the blackboard. All right. So here's probably some of you are already familiar with this theorem. Let script f. Now this script f should not be confused with that script f there, okay? This particular one. So visualize this, and this is the standard familiar picture that you may have seen in books. So the strip between -1/2 and 1/2 looks like this. And if I draw the unit circle, not very well drawn, but anyway, let me draw it again. And this time I might want to make sure that okay, this is a better picture. Okay, there. So these points, so this is the unit circle, and so the region mod z is bigger than or equal to 1 is outside of the unit circle, right? And it has to intersect with the fact that the real part has to be between -1/2 and 1/2. So this is the region we're talking about, this region. So the picture looks like this for f. And this particular region is a fundamental domain for SL2Z. Or, people just say for SL2Z, but for the action of SL2Z on the upper half plane, okay? For SL2Z. Acting on H. Now, what is this point here? This point here is, of course, I. This point I'll let you figure out. It's really cube root of unity. 1/2 1 plus root minus 3 over 2. So cube root, let me just call it cube root of unity, rho, and this will be rho squared. So these are cube roots of unity. So these points here. So how do you prove this? I'd like to show that this is a fundamental domain. To prove this, we need a little lemma. And the lemma is fix z in the upper half plane. The set of integer pairs CD with CD and mod CZ plus D is finite and non-empty. Okay, so let's see how to prove this. So the fact that CZ plus D is less than or equal to 1, so let's write Z as x plus IY. The fact that CZ plus D is less than or equal to 1 is equivalent to CX plus D squared plus Y squared plus C squared Y squared is less than or equal to 1. So in particular, C squared Y squared is less than or equal to 1. Which means that the absolute value of C is less than 1 over square root of Y, keeping in mind that Y is positive. And then they're only finite, so that means that they're only, C is an integer, remember. There are only finitely many integers in any bounded interval, therefore C is bounded. And once C is bounded, we go back here and look at mod Cx plus D. So C is bounded, so this is mod Cx plus D is also less than 1. So which means that minus 1 is between Cx plus D and 1. So Cx plus D lies between minus 1 and 1. And that means that D has to lie between (1 minus Cx), minus 1 minus Cx, and 1 minus 1 minus Cx. Therefore, D is bounded. Because C is bounded. So in terms of x, so this is all as a function of z. So D is bounded. And the point is that when CD is 0, 1, when C is 0 and D is 1, there's at least one point. So there's non-empty. CD equal to 0, 1 is a valid point, satisfies that, is in our set, and therefore it's not empty. So this is this little lemma that I'll need along the way. So just keep this in mind as we proceed with the proof. Okay, so maybe I have to rub this off. I was hoping to keep these conditions on the board so that we can see. Oh, at least I could mention that our goal is to show that this is a fundamental domain. The boundary of the region consists of this vertical line here, which is a smooth curve, this vertical line here, and this arc, which is also smooth. So, okay, so the last condition of the criterion for being a fundamental domain are satisfied. Yeah.
This mod of Cz plus d is strictly less than 1.
What is it? Cz plus d is strictly less than 1. What about that?
Strictly less than 1.
Yeah.
And that set is not if there's one.
Oh, I don't know. I mean, it's not clear. It may or may not be. Yeah. But fortunately, we won't need that kind of finer result that you're asking for. Yeah. It may be empty, actually, in that case. You can choose your y very small, very, very large or something. Could be. All right, so let's try to prove our theorem. So, proof of theorem. So as we already observed, if I have a matrix A, B, C, D, the imaginary part of gamma z is nothing but the imaginary part of z divided by mod Cz plus d squared. So since C and D are not both 0, because there's an element as C and D are not both 0, not both 0, we see that the function Cz plus d squared attains a positive minimum as gamma ranges over SL2Z. In fact, I mean, by the lemma, there are only finitely many such that Cz plus d is less than 1. Therefore, when you look at this particular thing, this quantity here, eventually for infinitely many, for all but finitely many, this is at least bigger than the imaginary part of z. Therefore, it will attain a positive minimum for as you range over these elements. We may choose, so use the lemma. So we may choose gamma such that mod Cz plus d is minimal. As we range over Is it clear to everybody? So you see the point is that this quantity here is bounded by 1 for all but finitely many, and therefore this is bigger than or equal to the imaginary part of z. This quantity here therefore attains a certain minimum. All I have to do is check those finitely many things, and as C and D range over these lower coordinates of the matrix. Okay. So once I do that, there's a specific gamma where it's thus for this choice of gamma, for this gamma, imaginary part of gamma z is maximal in absolute value, of course, is maximal. And if necessary, so I'm in the upper half plane, I'm trying to find a fundamental domain, I can always shift by the translation so I can make sure that the real part of z is between -1/2 and 1/2. So by shifting, we may ensure by translation see all those translations are in the SL2Z group, right? 1 and 0, 1. By translation, we can ensure that the real part of Z is between minus a half and a half. Okay. So we claim that gamma Z is actually, for this particular choice of gamma, we claim that gamma Z is bigger than or equal to 1. So that will put that point gamma Z in here. So suppose not, then W equal, put W equal to gamma Z, then mod W is strictly less than 1. Now remember the transformation S, which is 0, minus 1, 1, 0. It has the effect of taking W to minus 1 over W. But the imaginary part of SW is the imaginary part of W divided by mod W squared by our usual calculation. But mod W is less than 1, so 1 over mod W is bigger than 1. Okay, so this is bigger than that. Therefore, the imaginary part of S gamma Z is bigger than the imaginary part of gamma Z. Now, but I chose my gamma such that the imaginary part of gamma Z is maximal. That was my choice here, using that little lemma. And therefore, this is a contradiction, and therefore we indeed have the claim that I'm making, and therefore that point gamma Z is indeed in here. So every point in the upper half plane is equivalent to a point in this particular region. Okay, so contradiction implies that mod gamma Z is indeed bigger than or equal to 1. So by suitable translation, I made sure that it's between minus a half and a half, and now I've proved that it's in this region. So that shows that every element is gamma equivalent to some point of that. I am kind of running out of time. Let me just see what I have to do here. So what I'm going to do is I will, Karam Dev will take over the second part of this proof to show that no two interior points are equivalent. Okay, so there's one more thing to check, and I'll leave that for him to do together with your participation in the afternoon. So that more or less shows that this is a fundamental domain for the action. Now, as I mentioned, the fundamental domain is not unique. If I were to take this region and apply any element of SL2Z to it, I get another region which is nice analytically transformed to another nice connected interior region, so that'll also be a fundamental. So you can apply any element of SL2Z to this fundamental and you'll get another region. So in particular, let's see what happens if I apply the transformation S to F. It turns out that that region looks like this. This region. So this region, this is unbounded, so this is now a bounded region. So this bounded region is also a fundamental domain for this action. Okay, so this is S applied to F, that little region. And you could shift, you could move, you can do all sorts of interesting things. All right, that is one part. So this is for the full modular group. And so the natural question is, how do you determine fundamental domains for other subgroups of SL2Z? And so let me try to give you the general recipe of how one goes about doing this. So theorem. Let gamma be a congruent subgroup of SL2C. So it's a finite index with minus identity being an element of gamma. If G1, GR are the coset representatives of gamma in SL2Z, then a fundamental domain for gamma acting on the upper half plane is given by T sub gamma, call it, so you take the standard fundamental, so this is often called a standard fundamental domain. You take the standard fundamental domain script F and you apply, well, the inverses of these coset representatives. So you get regions. These could be patches all over the place. Sometimes you'd like to have a nice looking patch, but it doesn't matter. Each patch, each bit is nice connected interior, so the interior is connected, right? So that's that part. So this is what you get is given by this. Yes. And so how do you prove this? Okay, there are these three conditions that we have to check. The last one is the easiest one because the last condition is about the boundary being smooth curves. And so every time you apply this automorphism GI to the boundary, you're going to get smooth curves for each of these bits. So there are only finitely many. There are only three curves that you have to look at for the fundamental domain. You're going to apply this, so you're going to get three for each bit. And so that's okay. So clearly number 3 is satisfied. So how to show that, firstly, that every point in the upper half plane is gamma equivalent to some point here, and no two interior points are gamma equivalent. These are the two things we have to show. So let's do the first one. So any z, take any z in the upper half plane. We know z is SL2Z equivalent to some W in the standard fundamental domain, right? I.e., there exists there exists, what did I call it, tau? Okay, there exists tau in SL2Z such that tau W equals tau Z. Okay, there's.
I have a doubt actually. So the way you define that region, D of gamma, so why the interior is connected? I mean, it might happen that it will be union of some connected interiors.
I mean, yeah, it's connected interior. So, what am I trying to say when I say connected interior? What I meant is, I mean, you're worried that one could be in fact disconnected. I mean, one could be over here and one could be over here. Yeah, there is a. That's right. So. Yeah, there's a little bit more to be done on this. I think this is why Shimura belabors this point.
It has to be assumed.
It has to be assumed, yeah. I mean, for the purposes of what we're going to do, it's almost irrelevant because you can work on each patch. Who asked the question? Was it you? Okay, yeah. So you could work on each patch for the purposes of the thing, but it's not going to be terribly important. However, there is a kind of a smooth compactification that is needed as when we really want to do arithmetic on these Riemann surfaces. There's a smooth compactification that's needed, and for that purpose, we need to assume that this is the case. Yeah. So for the purpose of this particular course, this kind of result is enough because for the manipulations we're going to do with modular forms and higher levels and so on and so forth, integration and so on and so forth, it suffices to do it on each part. But if you're going to study the arithmetic of the coset space, like want a smooth model for that, one needs to do a little bit more work. So let me mull over this a little bit more later and then get back to you. But for the time being, we'll just assume that it is the case.
So we are assuming what?
We're just assuming that there is a nice fundamental domain which has a connected interior. Yeah. As I have it right now, this is in patches. Each patch has a connected interior, and maybe that's good enough for our purposes, but for the purposes of arithmetic and algebraic geometry, that may not be enough. And that's why, Shimura goes to pains to make sure that that's the case. So I'll get back to you later on that issue. So for the time being, we'll just assume that it's the case, or that that there exists a fundamental domain of this shape. Yeah, it's a subtle issue. We'll have to deal with that. Okay, so at least we can formally verify that any z is in fact gamma equivalent to a point here. So that's easy enough to do. So we start by looking at this. We know that z is SL2z equivalent to some w in the fundamental domain. So you can take this tau, which looks like this, and then tau is an element in SL2z, and since SL2z is a union of cosets of gamma, we can write tau as gi times gamma for some I. So gi, well, I say gi inverse times gamma for some I. So that gamma z then is equal to gamma z is equal to gi inverse tau z, which is gi inverse w, which is of course in our df. Sorry, I'm writing very small here, but gi inverse ww is in the fundamental domain, so it'll be in this. So it's not difficult to show that every element in the upper half plane is gamma equivalent to some point here. So that's not hard to do. Okay, so that part's there, and if again I will leave to Karamdev to show that any two interior points are not inequivalent. Okay, so that's and you're right that there is more one more issue. Let's see. Yeah, so this is actually not totally trivial to show that no two interior points are equivalent. So it's not totally trivial, but that's basically the philosophy. Now, to at least give one example where this problem that you've mentioned doesn't arise, let me just do this, state this example here. Let's look at gamma naught of 2 in SL2Z. So we calculated yesterday's lecture the index of these groups, gamma naught of n, and this particular one has index 3. So we need 3 coset representatives, has index 3, and coset representatives identity S and ST. Okay, so that therefore a fundamental domain for gamma naught of 2 is given by these and when you look at in terms of pictures, so we have the standard fundamental domain for SL2Z here. By applying S, I told you that you get this region here, and by applying ST, you kind of get this region here. So it turns out that this whole region is the fundamental domain for the action. Now, in this case, because we could see that we can choose our coset representative so that it's all kind of glued properly, that's a non-trivial fact. I'll have to, show that there is a way to choose these representatives in such a way that you're not moving one patch to all over, to different places. So this has to do with the subtle points of compactification. Okay, now in the 10 minutes remaining, let me talk about the extended upper half plane. So the extended upper half plane is H star, which is the union of the ordinary upper half plane, plus all rational numbers, plus what's called the point at infinity. And these additional points are called cusps. So we take the upper half plane and we tack on these cusps, and now we get a larger set. We topologize H star. We make this into a topological space. We topologize H star by, in the usual way, for Z in the upper half plane, the open fundamental system of neighborhoods is as before, fundamental system of neighborhoods is as usual, viewing the point as in the upper half space in the complex topology as usual. For a cusp S, which is not I infinity, so S is going to be a real number, a rational number. So here we have the upper half space, and here's S. What we will do is we will take circles that are tangent to that point. So, but lying in the upper half plane. Okay? So these open circles, so they're open circles. We don't actually, no. You can take. It doesn't matter. I mean, take open. These are open sets. We have to have open sets anyway. So take these open things. You can. So we'll take S union. So let's call this circle C. C interior. So S, the rational number S, along with the interior of the circle, is a fundamental neighborhood of S. So these are the fundamental neighborhoods of these cusps, the rational cusps. For infinity, what we will do is we'll take these regions in the upper half plane with the imaginary part is bigger than y, these regions, and we'll call this as a fundamental system. So let's see here. Let's call these U sub c. So U sub c's, as c is ranges over positive real numbers, will be a fundamental system of neighborhoods of infinity. So together with this, we now extend the action of SL2Z. We extend the action on H star in the obvious way. So you have if you have a cusp, we just let it be CS plus D. So for S rational, we let the transformation A, B, C, D acting on S to be this number, and if CS plus D is 0, we interpret that as infinity. Okay, so this is this is a legitimate action. So check that exercise to check this is a valid action. And we can then consider H star modulo the action of any congruent subgroup. And again, this problem arises on how to describe this coset space. You'd like it to be a nice compact Riemann surface, and for that we need a little bit more to make sure that fundamental domain argument that I gave is not sufficient here, right? So this is turns out to be a compact Riemann surface. Notice that in the case of SL2Z, with the standard fundamental domain, so if I look at SL2Z with the standard fundamental domain, and now talk about H star modulo SL2Z, well, we have this point at infinity, and so these two lines are identified, and these two, when you look at the transformation S maps this line to this line. So these two are equivalent. These two are equivalent. So when you glue it together and then use that point at infinity, you get a Riemann sphere. So the H, this is just a Riemann sphere. And in the general case, it's a compact Riemann surface. Of course, there's a lot of complex analysis that needs to be filled in, which I'm not going to do. I'm almost kind of running out of time, so let me just make a few minor comments, short, brief comments about metrization of this space, because it's going to be important later on. The first person who thought about metrization of the space was Poincaré, because you see, if you have the ordinary complex numbers comes with a metric, and that metric you just cannot transport to these spaces, or these spaces for that matter, because the metric has to be gamma invariant. And in order to get a gamma invariant metric, Poincaré defined the following metric. So Poincaré defined a metric on H star, or H, let's just leave it at H, which is SL2R invariant. And the definition is the distance between two numbers, Z and W, is given by the inverse hyperbolic cosine of 1 plus Z minus W squared divided by 2 times the imaginary part of Z, imaginary part W. And it's a small exercise which I suppose can be done in the afternoon to show that if I have this turns out to be so I'll leave that for you. Exercise. And so this is what's often called the hyperbolic metric. And again, one can study this for its own right. There's a whole geometry that you can study, the hyperbolic geometry, which is very interesting. For example, here in this hyperbolic geometry, the angles of a triangle add up to less than 180 degrees in this geometry. And then one more point, perhaps. So we have a nice. So we looked at this coset space. We've now compactified it by this adding all these cusps, and it turns out it has a complex structure. What we mean by a complex structure is that every point has a neighborhood, which can be mapped homeomorphically to an open set in the complex plane. So you can kind of think of it as a complex manifold, and that's what we are now looking at it like that. And we have managed to metrize it. We can, in fact, also introduce a measure. The measure is dx dy by y squared is a SL2R invariant measure on H. So this is the measure that one uses, and if we are interested in calculating the area of the fundamental domain, that is just the integral the cusps are zero measure quantity anyway, so you get this. So this is the area of the fundamental domain. That's what when we talk about the area of the fundamental, this is what we mean. And it's a small calculation to show that this is actually equal to the index of gamma times pi by 3. It's not a trivial calculation, it's a non-trivial calculation. And maybe if there's time, that can be done. It's just checking whether you know multivariable calculus or not, and you can do the right Jacobian transformation and change variables and so on and so forth. So that's basically the summary of this particular chapter. I'm sorry I went over time, but in the afternoon we'll fill in a few details.